Yes.
Very good. So, all right, I'll start. First of all, thank you for the organizers to prepare such a great workshop. I went to some of the talks. I could not go to all of them. It started very early, like this morning. You know, as you mentioned, Johannes, I was up, you know, at quarter to 5 to make sure that I would listen to some talks. So, good morning from my point of view. Good afternoon from your point of view. I'm just showing here my new institution, UMass Boston, which is in a peninsula just on the coast with Boston downtown in the background. So I will be giving a talk about the S-wave scattering, locking, if you want, and the unlocking in resonant exchange processes. I will also give few things later on at the end. I added few topics. First, I want to do the thanks because I will forget otherwise. So the first one is my my student D Shu, or former student, he's now graduated. The work of Lionel Simbotin, and also, of course, the early work done with Alex Dargano a long time ago now. And these are all working on the atom ion and the resonant exchange systems. And later on at the end, I will mention a few things about an interesting system, C60 collisions. And this work was done with Vasily Karchenko. My student shared with Vasily because of the move of institution, Jonathan Smucker, which couldn't find a nice picture of him, and John Montgomery. All right, so motivation. Well, first of all, this is what the talk will be about. The first part would be about resonant exchange, but the second part would be just just showing some results on C60 colliding with an ion. And the reason for this work is just that we were looking for a common project with me and Vasily, and including my student. So. All right, let's start. So why, I don't need to actually, I should probably skip this after a whole workshop on atom ion. I don't think I need to convince anyone why these type of systems are interesting. But I just want to mention that, we started to work on that such a long time ago with Alex, and at the time, these kind of systems were really far from being even in the radar screen of experimental work. So, and again, there's many reasons why people also got interested. There's this charge hopping, which was also discussed this morning by Sadiq, and I will probably try to answer one question that was asked. Hopefully, we'll have time. There's mesoscopic ion, molecular ion, and there's Rydbergs, for example, Rydberg electrons scattering with atoms or molecules or in degenerate systems. So there's many reasons why people are also interested in these kind of systems. So what I'm looking at is really resonant exchange process, and those are very general. This can happen, for example, in spin flip, charge exchange, excitation exchange, and they involve a variety of long-range potentials. One of our cube for dipole allowed transition, one of our fourth, as we discussed just this earlier about polarization potential, one of our six for van der Waals interaction. So the behavior could be different, but on the other hand, the type of process is quite general. So these happens when basically you have two states that are degenerate at infinity, if you want, but there is an exchange energy or exchange interaction between the curves. So these are the curves, for example, for ytterbium and ytterbium plus, showing the exchange energy, if you want, in this shadow. So this is the exchange energy, and these are the two potential at large distance. So how do you describe this phenomenon? It's well known. It's just basically the sum of the partial waves of the S wave, not the S wave, sorry, the phase shift difference between the two channels A and B. And it's a very simple expression, can be derived by looking at the superposition and getting at the interference between the two channels, that the two paths that you're having. I will not go into details how it's derived, but that's a simple expression. The behavior in early days, Alex and I, we worked on those sodium plus collisions, and we could see that actually the what we call then the elastic, which is anyway, and the charge exchange had very simple behavior with 1/4 the square root of the energy, which is a Langevin-like behavior. And this is true over many, many decades of energy. So these were the early days. And a few years later, we did something similar, because at the time, Vladan Velucek at MIT was had some experiments on ytterbium. And so we did similar calculations. And, for the elastic part, we're getting the same behavior, 1/4 the energy to the 1/3. But some of the surprise was with the charge exchange, cross section. We found a very large variation with the different isotopes. And what was a bit surprising is that my expectation at the time was that at low energy, things in the Wigner regime, things would be quite different, because the scattering length, etc., of the potential would be quite different. But that at some point, as you increase the energy, higher partial wave would kick in, and what I was expecting is all those very different curves here to more or less come back to more or less the same value, the same behavior. But what we found out at the time, which was a bit unexpected, is that it looked like the S wave low energy regime seemed to dictate how the larger energy regime would behave. So that if this was low because of the scattering length difference, if you want, for charge exchange was small, it seemed to pull the whole curve down. And this was something that was surprising. But at the time, we just let it pass. But to explain that, one way to look at it is actually to look at the phase shifts. So to explain that, we just look now at the calculate the phase shift. In our case, what we did is we used a phase amplitude approach. And as we, people who remember some of the old textbook, you find out that the phase shift, of course, will depend on how big the centrifugal barrier is. For example, if the centrifugal barrier is below the incoming energy of the scattering, you will see that the phase shift can be described as the S wave phase shift, will grow like L pi over 2, and will have a L squared, if you want, contribution that depends on a parameter A here, which is actually something that probes the inner part of the potential. If you go at if the barrier becomes larger than the incoming energy, then the phase shift is a N pi, and the integer here depends on the partial waves, but it's something that is the number of bound state inside, if you want, plus a phase shift from coming from outside. And this phase shift coming from the outside, if this barrier is far enough in position and depends only on the long range 1/r to the n, will be the same for the channel A or channel B. So with that in mind, we can see this is just in a way a textbook representation of how the phase shifts behave. As a function of L for a given energy, the phase shifts start from L equals 0, the S wave, grows like L pi over 2, and then has a curvature, as we say here, inverse parabola. And then you hit some bound state, and then you have the outside phase shift that I was telling you about. So this is the behavior. And when you take the phase shift difference between two channels, if you have a high barrier, you'll find out that the outer part of both channel A and channel B just cancel out, and the phase shift difference is just an integer times pi. While if the barrier is low, the phase shift difference is only the S wave phase shift difference. The L pi over 2, the linear part, cancel out, and then you have this inverse, parabola type L squared, or LL plus 1 times the a difference that correspond, or parameter that correspond to the potential. So let's pay attention to this difference. We calculated this delta AL as a function of L. And what you find out is that there is a very small L dependence. To make life easier, we can therefore approximate this variation of this parameter A as the S wave value. So delta A naught, therefore not L dependent. That's one approximation that we can make. Furthermore, this delta A0, you can show that it depends on the potentials, but you can show that actually it is a fairly small value, which is also rather constant as a function of the energy. So we therefore can neglect the L dependence of delta A, and we can further neglect for a large range of energy its energy dependence. So these two approximations make life easier for us. So we go back now to the sum for the phase shift for the cross section, and because of the fact that we have an integer times pi for a large centrifugal barrier, we can truncate the sum from 0 to this big L, which is the maximum L where the centrifugal barrier is equal to the energy. And then we just transform this sum into we take the S wave out, and then the rest is just an integer, an integral. And we rewrite the cross section as the S wave cross section plus I would say the classical, and I will come back on that, the classical Langevin cross section, if you want, times a correction that we call the quantal function, correction function. So now with this definition, we can go back to our cross-section, charge exchange cross-section for the ytterbium plus, and plot how this function f would look like. So here I plot all the same cross sections that are in this lower left panel. This is for the various isotopes here. And from this, if you subtract the S wave cross section, and you divide by, and basically you also divide by the Langevin, you get this function on the right panels. This is the function that goes between 0 and 1. This is on a log scale. So you see that this function, this correction function, varies a lot from one isotope to the other. It goes, if it's equal to 1, you basically get the classical behavior. If it's very suppressed, for example, this is extremely suppressed, you have a very different behavior. So we want to understand, this is now all of those functions plot on the same graph, and we want to understand them. The behavior, again, this is on a log scale for the energy, and the function should be between 0 and 1, but because of resonances, of course, it can go over 1. 1 is what you would say the classical behavior, the Langevin behavior. At large energy, this function goes to half, 1/2. And in a way, you could say that it's because the sine squared of something which is random gives you basically 1/2. So, so this is expected. But we want to explain what's going on in this range of energies. To do that, we just look at our function f which you can express in this manner. It's with the approximation that we just keep the delta A0, which is also energy independent to a certain extent, but anyway, we keep it energy independent. We can then do look at the expression for F, and we can do it analytically. Sorry, and you find out it's a very simple expression. This function F depends on the value of this delta A0, but depends on the phase shift, the S wave phase shift difference at a big, on a big range of energy. This behavior can be understood in terms of the fact that the phase shifts are locked, if you want. If L, or big lambda, which is big L plus 1, becomes big enough, you get almost a randomization of these terms, and then F goes to equal to 1/2. So let's see how things work out. So I take one isotope. This is for ytterbium 168. In black, this is the calculation, the full calculation. In green, this is the simple expression I showed before, but with the S wave phase shift difference computed with the potentials. And as you can see, it is quite amazingly fitting, except maybe at higher energies, the whole range. One thing we thought is like, well, can we use that to do some fitting? So what we did is fit the calculated black curve in this small range of energy from 10⁻⁵ to 10⁻⁶. And if you use that, you can then say, I will get parameters, 2 parameters from that. And then from those 2 parameters, you can extrapolate at low and higher energy. And this is the dashed line. And as you can see, the dashed line is actually more or less on top of the exact results. So again, with a small range, fitting in a small range of higher energy data, you could actually extrapolate at much lower energy. You may notice that I don't go to very, very low energy, because in some ways the Wigner regime cannot be predicted by this method, this approach. How does it look for the cross section? Well, this is the same thing, but now it's the cross section. As you can see, this is the fully calculated cross section. The green one is using the calculated S wave, but the simple expression. And the fit is again the red dash line. As I mentioned, the red dash line, the fit doesn't explain the Wigner regime. You can see that it explains very well the difference between the classical or Langevin cross section or capture cross section and the quantum calculations. Well, this was one example. Let's look at other examples. We did the same thing, of course, for ytterbium 170 and 176. You see here that this is closer to 1, and again, we get the same overall results, that the green curve is very close to the black calculations. And again, if you do a small, you do fitting in this small window, the red dash line is in very good agreement as well, except maybe at higher energies here. We did that for another system, isotope, which is more suppressed, if you want, where there's a larger correction. And again, we get very similar results, that the green curve, which is the simple expression, but with the exact S wave calculation, is in good agreement with the exact black curve. And the fit in the small window here, again, is in pretty good agreement with the green one. Here are the cross sections, the corresponding cross section. The 170 corresponds to something which is very close to I would say the Langevin or classical regime, you see that is very close to the Langevin cross section, only a small deviation. And again, you see that the Wigner regime is not explained by this the simple fit, but we get a very good agreement. The same thing is true with 176. You get some corrections to the Langevin if you want. And one thing I wanted to mention about the fit, the locking and the unlocking. What I call the unlocking is when we are starting to get this change from you get when the cross section is starting to go to have a fluctuation here. I can go a bit in details about that if I have time later. So just to play with that, we have also used a different model potential, and by varying various parameters of the depth of the potential, etc., to just get more extreme cases. And here I just show three different cases just to show the again the behavior. This is something which is similar to what I showed in previous cases. You have a small, it's basically close to the Langevin regime. Here, this is where you have a very, very large, in this panel, very large correction. And this is when the locking of the phase shifts is good here. And then here it's when the two S-way, the phase shift of the two channels start to not be in step anymore. And then suddenly it starts growing, and you get, after that, oscillations. This is a very suppressed regime, if you want. The cross-section is smaller, but you get a very good agreement between the exact calculation and this simple approximation. Of course, this work, when this work was initiated a while back, there were also experiments, and I think those were also discussed in this this workshop. Work on lithium in ytterbium plus, where the scattering length difference was in a way a parameter to understand the experiment, and also in rubidium strontium plus. And the locking of the phase shifts was also mentioned or advanced as an explanation in the experiment by Roy, and so in a way there's already experimental evidence that this is going on. At the time, as I mentioned, we were working on the same thing. So, and we showed that the exchange cross section was basically the Langevin corrected by the phase shift difference, the S-wave phase shift difference. And again, this could be applied to any type of power laws potential, 1/r³, 1/r⁴, 1/r�6. It's only the capture cross section would be different, but the behavior would be the same. So that was the first part of the talk. Let's see how much time I have. I cannot see on my screen.
You don't have any more time.
Really? Okay. I would be very short.
2 minutes, yeah. So
2 minutes.
Much, yeah.
All right, 2 minutes. So just show you something that a very different type of work. We're just trying to find out what happens when you have an ion colliding with a C60. And the reason for that, as I mentioned, is because one of my former student, Jonathan, we wanted to get a project that both me and Vasily could work on with him. So we found that there were experiments on C60 charge exchange and C60 resonant charge exchange with C60 plus, and also with collision with ions, atomic ions. So what we did is we did some calculations and some models, and I just want to show the results. They are actually described in this manuscript. but it's C60 colliding with nitrogen plus, neon plus, or oxygen plus with a charge exchange. We also looked at the fragmentation. So when C60 collide with, it should be X plus, sorry, you will get you may extract C2 from the collision. So basically, instead of getting C60, you get C58 plus, and then there's a C2 that is going out. And these were the data. These points are from measurements from people in 1992. And we were able, with a simple Landau-Zenner model, to get a fairly good agreement with those curves. This was for oxygen colliding with C60, oxygen plus. This was for nitrogen plus, again, a fairly good agreement. And this was for neon, where the agreement is not as good, and we're trying to understand better why is that. But these were with simple models, Landau-Zenner type. But I won't have time to go in details. I just want to conclude with saying that I went over the simple explanation for the resonant processes, that there is a link, which was surprising at the time, that the S wave cross scattering was actually dictating the cross section over a large range of energies. And the interesting thing with that is this could be used to fit, a simple fit could be used to get information over a large range of energies, especially in cases where the experiments might be very difficult to do at very low energies. You can still get a lot of information if you can do it at larger energies. And with the C60, it's a complicated system. We are working now on the C60 and C60 plus collisions, where you can have interesting dynamics, where you have a bridge between the two C60 being formed when they collide. So we're starting to explore that. And with that, I will stop here. Thank you.
Oh. Yeah, thank you, Robin, for a very clear, nice talk. There are certainly questions. Olivier?
Hi, Urba. Good to see you.
Okay, I'll stop sharing. Okay, now I see what I was doing. Okay, hi.
Right? Okay, that's good. So thanks for the nice talk and very clear and pedagogical. So I was about to ask a question, but it was mentioned in your conclusion. This, as you said, is very general, and even it should work with quasi-resonant system. I mean, you talked about exchange reactions, which of course you need resonance. But what you described is fast unlocking indeed does not depend on that, right? It depends on the fact that you would have a quasi-degeneracy in the sense that a small difference between the two channels compared to the strength of the interactions, correct?
Yes. So this should be applicable to a quasi-resonant system collision. And then in the regime where, of course, the scattering energy is much larger than the energy difference between the two.
Maybe my other question, you were proposing a fit in some kind of intermediate energy range.
Yeah.
The point is that would you have fit, if you would have fitted your thing a little bit on the left, on the right, what would have happened? I mean, my suspicion, which is because we are friends, so I say that, is that you chose, you kind of made several trials and you chose the zone where it works. And so this is for fun that I'm saying that, but in reality, is it indeed depending on the range where you fit, or what is the situation there?
So we did. So the reason we used that range is because we thought we tried few other ranges. There is a variability, but the reason we went for this range is because there is a lot of partial waves, and if you try to, there's a lot of partial waves and the effect of the shape resonances. So if I try to fit the calculations which have shape resonances, and I try to fit that, I would need to smooth it. So I was just to make our life easier. We just didn't want to deal with the smoothing. Where do you, if you have shape resonances, where do you do this? How do you smooth your curve to do the fit? So that was the main reason. But if you there would be a variation, but I think within, I would not, I think it's within 5 to 10% of the cross section. It would not be a big difference.
Okay, thank you very much.
But okay.
Are there more questions? Roy.
So Robin, thank you very much for the great talk. It's very clear. So would it be correct that the fact that we do see evidence for the fact that there'll be shape resonances there, even at very high frequencies, is the same? I mean, it's the outcome of the same mechanism. It's the fact that the S-wave behavior still persists over larger energies. And in that case, you know, one question could be, and I don't know the reason for it, but when we try to numerically look on whether Feshbach resonances exists at these higher energies, we couldn't see evidence for them, but shape resonances did. Is there any insight you have for that?
I think one could use these simple curves in a way to, I would say, because again, it's a difference of S-wave phase shifts, but you could use that in a way to establish a background, and then from that calculate or the position. If you have a resonance, then you could use that to really adjust your potential to have the resonance at the right place. Because what this simple treatment will have no resonances in it. Yeah, it doesn't have that. I'm not sure if I answer your question there, but I think it could be used to calibrate the potential difference, and therefore find once this is calibrated, and if you have one shape resonance somewhere, it would then probably fit the potential difference between. So if you have I don't know, a D or whatever way, shape resonance, you could then probably establish the potential, the difference between the potential. I don't know if that would be very useful, but once you have that, you could in principle predict the others.
Okay, so next question will be by Sadiq. So you guys can now, you know, resolve the open questions.
Oh, well, I have just one question actually. So the you mentioned somewhere in the middle that various power law forms could be of potentials could be actually this scheme should work for.
Yeah.
All of them, 1 by r cubed, etc. What is the story for 1 over r6 actually? That's also.
Well, you know, so all I want is one experimentalist to actually look at rubidium spin flip between rubidium 85, rubidium 87, and do that at higher temperature. Everybody is looking at S wave, very low nanokelvin or lower. I would love someone to just do experiments, you know, from 1 microkelvin all the way to 1 Kelvin if possible, and see what they get, and that should fit this expression. It's just that I don't know, I haven't seen the data for spin flip between singlet triplet. So prepare everything in the mixed state, which is, you know, the singlet mixed state that has you can have a spin flip in your system, and you should be able to detect that. But I don't know if that answers your question, but one thing I wanted to mention is, Sadiq, when you gave your talk, there were questions about charge hopping and the interpretation of that, and I just wanted to mention that when you do the treatment that we do is really a binary collision. So when you look at a binary collision and you calculate the cross section, everything is included there. The hopping conductivity and so on is an attempt to describe the many-body system, where so when we do the calculation, it's it's not that we're not doing the time dependent, so we don't looking we're not looking at as an atom and an ion collide that the charge can jump many times. This is all included in this time independent treatment. You get a cross section that includes everything for the binary system. So it's a quantum calculation.
Sure.
But no, there were some questions this morning
so the question
about
was
the
actually the question actually was about your 2000 paper.
Yep.
And the question there was that the distributions of the ion and the atom were very, very separated in those. So let me try and see. Oh, I think he's left. And that is what I didn't want to comment on, actually.
Okay.
Because I mean, I knew you were coming on next, and I said, let Robin take that. Yeah, but I mean, clearly what we have done is taken a time-dependent thing and made it time-independent via a certain prescription. And now one has to see how robust this prescription actually turns out to be.
Yeah, but the treatment in Massey and so on, all that is for binary collisions,
Sure.
and when you do the full calculation, hopping and all, charge exchange, all that is included in the calculation. So there's no, which is what we did together also.
Yeah.
I just wanted to add a small comment about what you were calling for rubidium 85, 87.
Yeah.
I mean, you will find the result. I mean, what you describe is just very robust. I mean, you just have two potentials, difference of phase, which is fixed with the energy, and then you will find the right result. Now, of course, now that the experiment is done at very low energy, then in a way you don't care anymore about the experiment at high energy, because you would use it to extrapolate toward low energy. So you already got the result at low energy. So who cares? You know what I mean? But what I'm saying is it's a very solid statement. And so there is no reason why it should not work. So
No. And I agree. I mean, for me, it's just that, if you look at this 2018 paper, this PRL that we did, we showed there the results for rubidium, what it should be. So we did the calculation, and we showed this is what you should get. But of course, it would be great to see an experimental validation, but I don't need the validation myself. I'm pretty sure it's pretty strong. So, but it would be nice to see it.
So I think if there are no more questions, then we close this session. And actually, also we close the workshop. So, Michał, you wanna?